Hi guys, I have here a classic Sony Betamax. This is an SL5200, the prominent Betahifi. This is the machine that started the hi-fi recording revolution. It's the first hi-fi half-inch video cassette recorder ever made by any company. Prior to this machine, some of the VHS manufacturers they had experimented with linear, what they called Dolby stereo, which basically took the AM radio quality soundtrack, linear soundtrack, and split it into and turned it into basically 2 tracks of AM radio. Sony said, no, we're not going to make a linear stereo beta machine. We need something better. This is it. This is the machine that started it all. This is my machine. I've had this machine. I bought it new in 1983, and it cost a small fortune. This machine was probably $1,400 or $1,500, and back in 1983, that was a lot of money to spend on a VCR. And that was wholesale, because I bought this when I worked for the Sony Corporation. So I bought this thing at wholesale, and it was probably about $1,400 by the time I paid tax and stuff. It's got the good old voltage, manual voltage synthesis tuner, where you tune each little channel in with a little multi-turn pot. Select your band, low, mid, or high. It's got a 14 position tuner. The hi-fi recording with level controls. I haven't plugged this unit in yet. We are going to plug this unit in. I'm going to give this unit a complete overhaul and make it work like new. This machine has not seen service in probably 30 years. So I don't know what to expect when I plug it in. But plug it in we will, after I take it apart and inspect it. Before we get into servicing this unit though, I do have a full set of manuals, and I think what we'll do is we'll do a deep dive on how the Betahifi system works. A lot of this information is also valid for VHS hi-fi, although the way that the VHS companies had to lay the recording down, they had to use separate heads for recording the hi-fi soundtrack because they didn't have enough bandwidth to do it with the conventional video heads, which is something that Sony was able to do on this. And when you see the inside of this machine, you'll be quite impressed. It looks very, very similar to the 3/4 inch machine that you see the first shot of my opening logo with the big drum in it, my logo theme. That first shot you see is my Panasonic 3/4 inch machine. This machine, when I get the top off it, you will see that it looks very, very similar the way that the mechanism is laid out, because the original Betamax machines were essentially 3/4 inch machines scaled down to use a 1/2 inch tape. But let's get in and look at the manuals and see how the signal is laid down on the tape, and then we'll get into servicing this thing. First, to understand how the system works, and in general how video recording works in general, for those of you who don't understand the magic of putting video down onto tape. Basically, you have a head scanner that scans the tape and produces diagonal tracks. So your video tracks are recorded. Now obviously they're not at this steep an angle, they're more along the tape than this, but you get the general idea. And there's a control track at the beginning of each of the A fields. There's a pulse that tells the head which track to start playing. So every time there's a pulse, it knows that this is the A field. So you would have your A field here, and then this is your B field, and then your A field and your B field, and your A field and your B field. And in conventional videotape, your audio track is recorded along the top edge of the tape, your control track along the bottom edge, and then your video track in the middle. And on conventional stereo VHS machines, what they did is they split this track in two and put two very thin tracks. What they did on the Betahifi system is they added the video and audio tracks together and recorded them by the video heads. And how they did that is they placed the audio onto 4 separate carriers, placed between the down-converted chroma, which is 688 kilohertz, and the luminance, or the Y signal, which is also FM modulated. As it states here, Betahifi system records audio signal on the video track on which video signals have only been recorded in the past after FM modulating the audio signals. Recording audio signals by FM, recording playback, results in excellent frequency characteristics, less noise and distortion, and wide dynamic range. And it's using the same 2 video heads and the same relative tape to head speed, and it'll be very high compared to the slow speed of your linear track. And it tells you down here, if you're using Beta 3, your head width is 33 microns compared with the track width of 19 microns. So because, unlike on VHS, the VHS machines used 4 heads, they used a wider head for the SP and a narrower head for the EP, and 2-head machines just used a narrower head. While on Beta they didn't. They used a 33 micron head, but when recording at the slower speed, there's actually some overlap, as it shows here. 1/3, if you're going into the Beta 3 speed, your track width is only 19.5 microns, but your head width is 33 microns. So 1/3 of the head reproduces the adjoining channels. Because your FM signals here are lower in frequency than the Y signal, your head azimuth losses cannot be anticipated. In other words, the crosstalk between them would cause interference. So what they had to do to compensate for that was they actually had to select 4 carriers. And that's what they have done. If they only used 2 channels, it would be fine at the Beta 2 speed because there's no overlap. But in the Beta 3 speed, there's overlap between one head and the other. So you would be picking up both signals at the same time. So what they ended up doing is they ended up creating 4 separate carriers at 1.38 megahertz, 1.53, 1.67, and 1.82. As you can see, these first 3 here are actually in the AM broadcast band. 1380 kilohertz, 1530 kilohertz, 1679 kilohertz. But they're FM modulated, and because of that, the AFM board was quite well shielded, because if it wasn't, if you had a local AM radio station that was, say, broadcasting at 1530, that's sitting on the same frequency that is being used for the B track for the left audio. So that could cause interference. So the whole system was quite well shielded to prevent that. As you can see here, they compare the distortion and dynamic range with the conventional soundtrack and the wow and flutter of the conventional soundtrack and frequency characteristics with the hi-fi soundtrack. The conventional system could reproduce sound for approximately 50 to 7 kilohertz, 50 hertz to 7 kilohertz, whereas the AFM system could produce sound from about 20 hertz to 20 kilohertz or 20,000 hertz, so a superior sound quality with 80 dB of signal to noise ratio. That brought the sound quality from these Betahifi machines almost to the same type of quality that you would get from a digital recording. Almost, not quite, because they ended up using a companding system, and they went with a DBX type system. So you sometimes could hear it working in the background. So it was very good, but it wasn't as good as a full digital recording. But even at that, a lot of people, including myself, we used to use these machines as high-end audio recorders. So basically this is how they recorded the signal. The luminance, or the Y signal, coming from the FM modulator is, or the Y signal is passed into an FM modulator, and they actually increase the frequency range a little bit on the Y signal to give a little bit of space between the chroma and the luminance. They shifted it up by, I believe it was 400 kilohertz in frequency, just to create a bit of a gap between the chroma and the bottom of the Y signal. So they put a filter on here to notch out the lower sideband and create some spectrum, and then you add in the low frequency conversion chroma signal, because the chroma on an NTSC signal is normally centered around 3.579545 kilohertz, and they convert that down to 688 kilohertz for recording, because direct recording is not possible on half-inch beta type and VHS type machines. There's not enough head speed. Direct recording was done on 1-inch broadcast, but all the video cassette formats, including 3/4 inch, used a color under or a heterodyne system. So your color is converted down and it's mixed back in with the FM modulated video signal. And the audio FM signals are also added here, sent to the head amplifier and recorded on tape. On playback, your head picks up the signal from the tape. It's amplified. The signal is stripped off. The chroma goes towards the chroma circuit. The AFM signal goes to the demodulating circuits. Again, we put a high-pass filter to filter out any of the chroma that may be left over and any of the AFM signals, so that they don't hit the demodulator and interfere with the picture, and then you end up with your Y signal. Pretty straightforward. We'll look at a few more of these prints before we actually tear into the machine. So basically this block diagram shows that you have an oscillator and your audio signals go in through your limiter. Your voltage controlled oscillator generates your 1.53 and 1.68 megahertz signal. Goes into the bias circuit and bandpass filters, and you produce your 4 separate carriers. This BM1 and BM2, this is I think this is a balanced modulator if I'm not mistaken, and generates your 4 carriers. You have 4 adjustments for the 4 carrier levels, and then they go to the rotary head. It was quite a complex system. Nobody else had done this before, and there's a lot of discrete circuits in here in this particular machine. It was, again, when we first saw these things, you had to kind of wrap your head around how they were doing things, because it was completely different than the conventional way of thinking for how video recorders operated. I actually had to stare at this block diagram for a minute to figure out what the heck they were doing here. But basically what happens, I'm just going to show you the A channel for the A head. The B channel works exactly the same. There's 2 sets of switching here, and it took me a few seconds to figure out what exactly they're doing here, because these switches appear to be doing exactly the opposite. And until I looked at the circuitry down here, we have our RF switching point, our RF switching pulse that comes in, which basically tells the unit which head you're on, whether you're on the head A or the head B. But there's also the PG pulse, which is your pulse generator for your head switching. Video heads are switched. They're not switched. Many people would think that the video heads are actually switched during the vertical blanking, but that's not correct. They're actually switched before vertical blanking, about 6 lines before the bottom of the picture. And the reason for that is, if your head switching pulse was to occur during vertical sync, it could disrupt the sync and cause the picture to roll. So you want the head switching to be completed prior to the actual handoff from one head to another. So there is a slight overlap on video heads where both heads are actually in contact with the tape for just a split second, a few lines before the switching takes place. And that is what they're doing here. So basically what happens is the signal is passing through its respective amplifier and ending up in the demodulation circuit. Here's our 4 demodulators and our switching for audio out. And what's happening is at the head switching point, the switch switches from one side to the other, but it does it before the switching is done for the audio. Otherwise, you would have a buzz in the sound. So I was looking at that, trying to figure out why they have a set of switches here and another set of switches over here. And then I realized what they're doing is one of them is triggered from the RF switching point, and the other one is triggered from the PG switching point. And that is what they are accomplishing. Over here we have our dropout compensator. Dropout compensator, what that does is if the carriers were to drop out, if there was a tape dropout that would cause a bunch of noise to appear, what happens is it mutes the audio. It shuts the audio off momentarily, and you end up with just no sound as opposed to noise. It's, again, quite the circuitry. This was the first generation of hi-fi machine, and it was overly complex, and these are all handled by individual components, whereas on later models it was all buried in one IC, and you didn't care because everything was just all in one IC. And here's the text that goes along with it that explains what they're doing. The 8-channel RF signal output by the playback amp is input to the 1.38 and 1.68 bandpass filters where F1 and F3 are removed. The B-channel RF is input to the 1.53 and 1.83 bandpass filters where F2 and F4 are removed. Next, F1 and F3 are input to the balance modulator for conversion into the 1.53 and 1.83 megahertz signals, and a high accuracy 149 kilohertz signal obtained by counting down a 2.3916 crystal oscillator to 1/6 is input to the balance modulator. Therefore, F2 and F1 both have been modulated by the left channel audio signal, and F4 and F3 have both been modulated by the right channel audio signal, are equal frequencies. For this reason, step noise, a noise caused by variations in the direct current levels when the A and B channels are switched after FM demodulation due to frequency differences between F2 and F1 or F3 and F4, become a level that can be neglected. I know what you guys are waiting for. You guys are waiting for me to open this bad boy up, so let's crack the top off this thing and see what's in this beast. VCR of this vintage, this thing weighs, I'm going to say about 30 pounds. It's no lightweight. This is from back in the day when they knew how to build VCRs, and they built them to last. This machine would be about 33 years old, I guess now. I think 1983 was when this one came out. That's when I bought it, so maybe not a little bit before then, but around 1983. You see, I mentioned that the shielding in place here. We'll identify some of the components in here. We have our power transformer over here, our power supply board. Here's our rectifier diodes, filter capacitors. It's a regulator down here. This is our IF circuit for our analog tuner. No, this unit did not have an MTS stereo tuner built in. This is before stereo TV. What it did have is it did have a multiplex or MPX output, which was the multiplexed audio before de-emphasis, so that future MTS decoder units could be purchased to convert this to MTS stereo. I know the part you guys want to really see is the transport. So let's get the shield cover removed here. I'm running out of room. Can't get in there with the screwdriver. This thing's too big. We have to remove. Oh, the screw's already removed for that one. So that should be 1, screw down here. I think I've removed some of the screws because this thing's been worked on in the past. It's not like it's never been worked on. Take off the shield cover. This is the audio hi-fi board and all the audio circuits that I talked about before. As I was telling you, everything is discrete. So we have all these tuned coils. This is essentially an FM receiver and an FM modulator, an FM transmitter. Long before everything was integrated into one jungle IC. You call it a jungle because you don't want to know what goes on in there. Here we have resistor packs. Check this out. Yeah. There we have resistor packs. So these ones here without any markings on them, those are common. So those are just wire connectors straight through, and we have 4 resistors here connected. All discrete individual components. There's our AF demodulation circuit here. And over here is our AF dropout compensator circuit over here. And this one here is our audio frequency modulator. So separate components, very well built, very easy to service because you have individual parts. Take a look at the head assembly on here. I'll flip this board out of the way, and it should just tilt out of the way just like that. Now this is just the audio modulator, demodulator. There's another little circuit board over here, which is the signal. This is the preamp, and I believe this is the on the side here. This is the companding circuit. But here's our head scanner. That should stand up there somehow, I think. There we go. They even have a little stand up to lock the head in. Here's our scanner assembly. Check this out. It's a 3-piece drum. The entire center, here's the heads. That head's pretty dirty. Here's the heads. The entire center spins. The bottom of the drum does not spin. The top of the drum does not spin. The entire scanning disc in the middle scans. Later beta machines, this was just replaced by a slot that the head stuck through. But the earlier beta machines, they had this 3-piece drum assembly because the logic behind this was that spinning head would help lubricate the tape and it wouldn't stick to the head drum. And that's true. They never had a problem with stiction on these machines that they did when they went to the 2-piece drum with just the slot sticking out. But this cost a lot more to make, and it was much more difficult for a technician to change the heads on a machine like this because in addition to just changing out the head drum, he had to worry about eccentricity. This drum had to be absolutely centered down to microns, otherwise the picture would shake violently, which required a micrometer that was screwed down to the chassis. So it improved the stability of the picture and improved the picture quality substantially, but it made servicing these things something that only qualified people could do and qualified people with the proper equipment. Looking at the rest of this mechanism, we have our full audio erase head here, actually our full tape erase head over here, and over in this other block over here is our capstan assembly is down. I think it's there. There's our capstan. Our capstan assembly is right here. And we have our conventional audio head, which is down here, and our audio erase head. It's hard to see, but it's in this block here. Here's our adjustments for our audio head here. As you can see, they're all paint sealed. So there's no need to adjust these. They're set up. When a tape goes in, here's our pinch roller over here. This whole loading arm rotates to thread the tape up. We're going to be loading a tape on this, but I want to take a look and see the condition of the belts before I do anything. Actually, these belts don't look to be in too bad a shape. I fully expected them to be totally rotten, but as you can see, they actually, after sitting 30 years, they don't look to be in too bad a shape at all. So we may not even have any worn belts on this thing. This is amazing. this thing actually could work. Let's plug this thing in, turn on the power, and see if it turns on. Well, that's a good sign. We have power. We have lights. If I adjust the audio meters, you'll see noise. The audio gain here, that's from the tuner obviously, because there's no signal tuned in here. Shall we try putting a tape in it and see if it works? So this is the first time in over 30 years that this machine's had a tape in it. Let's see if anything works. Okay, that wheel is slipping a little bit, but that looked pretty good. It loaded the tape. Will it play? I don't have a monitor hooked up, but let's just see whether the tape actually starts turning. The tape is turning and the drum just sped up to full speed. I'm going to hook up a monitor and see if we actually have a picture on this thing. The moment of truth. Play. Oh, that sounds awful. Well, it's going the wrong speed. Let's try cleaning the heads on this thing and see. That part works. At least it opens and closes. We have a servo problem. We have a capstan speed problem for one. Let's try cleaning the heads and see whether we actually can get a picture off this thing. To clean the heads, I'm just going to use the good old tried and true method of a piece of paper and just wipe the heads. Just turn the head counterclockwise, which is the way that it turns. And I would say that there was a fair bit of dirt on that video head. I'm going to let it dry for a minute here because I don't want the tape sticking to the drum. We'll see if we can get it to play this tape back before I put in another hi-fi tape. This is not a hi-fi tape that's on here now, but let's see if we can get the machine playing before we get too involved and give this thing a total service. It would be nice to get this old beast up and running again. Okay, the machine should be dry now. Pretty good. We're not getting a picture because we're not going the right speed. Looks like our head drum is running at the right speed. It's just that the sounds like it's playing at beta 3, and this is probably a beta 2 tape. Oh, here we go. This recording must be in beta 3. Let's try our you can play back beta 1 tapes, by the way, with a switch. Tracking. Holy smoke, it works. It's not working right. It's not quite, well, I guess it is. I'm adjusting the tracking control here. Get a bit of a bending at the top of the picture here. You can see we're not quite in sync, but I think some adjustments and we probably will get this thing working. This is also a very, very old tape. Pause. Well, this is only a 2-head machine, so it's not going to have clear pause. We have beta scan. And scan back and forward. And that works. As you can see, the tape comes out on this side. It's the exact opposite of the 3/4 inch machine that you saw in my other video. The 3/4 inch machine pulls the tape out and around the head drum this way, and Beta pulls the tape out this way. But the machines are identical the way that they operate. The tape is pulled out here, pulled out by this guide, wraps around past the full erase head, goes around the head drum, comes off the drum on this side here through this guide, over the audio and control head, and over to our pinch roller, which is down here. You'll notice when I press the pause button, you'll see what happens. You see the pinch roller here being released. This solenoid over here is this solenoid underneath here. This is what's engaging and disengaging the pinch roller. Now you wonder what this little arm is here, right? What that little arm is if the take-up were to stop for any reason and the tape would become slack, there's actually a little magnet right here, and there's a magnetic leaf switch in here. When the magnet passes the leaf switch, it will put the machine into emergency shutdown. So if I play it, you can see that this arm is now resting up against the tape. If something were to stop the tape from moving, that would go slack and it would shut the machine off. Just like that. So that would prevent the machine from eating your tape. If this wasn't here and the machine did not shut off, you'd end up with countless feet of tape that would be wrapped up inside here, because if the pinch roller would continue to pull the tape, if the take-up spool wasn't working, you'd end up with tape all over the place. But this machine's pretty amazing. After sitting all these years, I can put it into rewind, and this thing's going to go into full speed rewind. Check this out. Here's our tape. If I go to rewind, and if I go to fast forward, rewind, play. This is from a machine that has been sitting for over 30 years and not been touched, and I haven't done anything to it other than clean the heads. Over here, this is our tape end sensor. How this works is on rewind, there's a metallic leader to the tape, and there's another one over here on the supply side. If I come up to this with something metal, such as a metallic screwdriver, you'll see what will happen when I approach this coil. It will stop. Right? You see that? The same as on rewind. If I put it into rewind and I approach this coil with something metal, it stops. What it does is it senses the metal leader. The tapes all had a metal leader. It senses the metal being in proximity to the coil. That's what triggers the auto stop on Beta machines. So here's an example of the auto stop working when I rewind a tape. See, there's the metal strip, the metal leader. Do it again. When the metal leader passes over the little coil here, it triggers the auto stop. This is a tape that I recorded. This is original camera footage in Beta 2 that I recorded off of a camera when I was down in Las Vegas. It's actually shots that are from my one of my videos that are up on YouTube. This is actually the original tape that was shot one time when I went down there. I went down a couple times. One time I had a broadcast set up, another time I just had a professional Beta 2 speed. This is the shots that I shot with that. As you can see, it's playing the Beta 2 tape's actually playing not too bad. Need a little bit of alignment on here. Our servos are a little bit out of whack, so let's work on getting that working. So to do that, we need to hook up a scope so that we can see what our RF envelope looks like, and I'm going to dig into the adjustment manual for calibration of the servos. Well, I got to play another tape here. This is an old tape that was done back in the early 80s on old Vidicon equipment. This is Vancouver. I found this old tape, dropouts on this thing, but I mean, this thing's actually playing it, and it's playing the soundtrack in hi-fi. Well, it was. it was a work in progress. It was playing. The noise is coming from the tracking lines on the tape. But I'm going to let this machine just run for a while here, because I think with time, let the bearings get a little bit loosened up because it's been sitting so long. I'm going to let this thing just play for a while, and then we'll try an alignment on it. If you guys want to hear the difference between the normal and the hi-fi soundtrack, just track it up here. Yeah, we'll get that going. Well, as you can see, here's the bottom of the machine, and these belts really do need to be replaced. Look at this one here. It's been sitting so long, it's got a flat spot in it. But look at our capstan belt. This is why it's drifting in and out of sync. It can slip. Whoops, I think we just killed it. We just knocked the belt right off. We'll just stop that and put the belt back on. Gotta see if I can find one that'll fit it. To replace the belts on this, just have to remove this bracket from the capstan flywheel. You notice that there's a frequency generator right on here. There's a magnet on here, and it actually monitors the frequency of the flywheel itself, not the motor. Got our new belt in here, and this one here is hopefully going to be okay. It's not tight, but hopefully it will be tight enough to run without falling off. You notice that the bearing has got oodles of grease on it. Here's our frequency generator, so keep all magnets away from this. And there's a little Hall effect device here. That's what monitors the speed of the actual flywheel, the capstan itself. Put that back on. Put the two screws back in that hold that in place. Now, it's not the exact belt. The original belt that was in there was a flat belt, and I put a square belt in. But it should be good enough for getting this machine running, because this old belt was just getting a little too stretched. May be able to shrink that a bit, but we'll see. But we'll try this one and see how it works. Power it back up, and see what happens. As you can see with this belt, it's nowhere near as loose as the other one. If I stop it, it'll start right back up. So it provides enough slip that it won't stall out the motor, but it's not going to really slip like the other one. It comes right back up to speed right away. So this belt is probably okay, at least in the interim. If we look at the servo board on this unit, we can see that this one's already had the modification done. All these Sony 5000 series, they had aluminum capacitors in here, little tantalum aluminum capacitors, and they all failed, so they've all been replaced with tantalums. So we know this is going to be good. The servo on here is going to be good. I'm going to get my manual out now and just go through the alignment procedure and make sure that everything is as it's supposed to be, and see if we can get this this bit of a problem that we're having every so often. It sounds like the drum is going a bit out of phase, and our switching pulse is kicking in, and you're hearing the head switching occur when it's not supposed to. And it's causing that 30 hertz noise to appear only in the left channel. So getting out the manual and actually look at this thing and see what's going on, why it's doing it. Seems to be possibly a problem in the switching, the head switching circuit.